Good morning, everyone. Today, I'm going to present Unit 2 of Artificial Intelligence, which focuses on problem solving and search techniques. In artificial intelligence, one of the most fundamental ability of an intelligent system is to solve problem efficiently and make rational decisions. Unlike humans, machine cannot think naturally. So we need structured method and algorithms that allow them to search through possible solutions systematically. In this unit, we will explore how problems are represented, how search spaces are constructed, and how different algorithms are used to find optimal or near optimal solutions. We will begin with state space representation and problem formulations, then move into uninformed and informed search techniques, and finally discuss game playing strategies such as the minimax algorithm and alpha beta pruning. These concepts are backbone of intelligent reasoning in AI system. State space representation. State space representation is the foundation of problem solving in artificial intelligence. Whenever we want an AI system to solve a problem, we must first convert that problem into structured mathematical model called a state space. A state represents a specific configuration or situation of the problem at a given time. The state space includes all possible states that can occur from the beginning to the goal. Every problem begins with an initial state, which is the starting point, and aim to reach a goal which represents the solution. The transition between states are performed using operators or actions. For example, in the 8 puzzle problem, each arrangement of the tiles represents a different state and moving a tile represents an operator. In a route finding problem, cities represent state and road represent transition. By representing problem in this structured way, AI system can systematically explore possible paths to reach the goal. So, in the problem formulation in AI, after representing the state space, the next important step is problem formulation. Problem formulations means clearly defining the components of a problem so that it can be solved by a search algorithm. A well defined AI problem consists of 5 key components: the initial state, the set of possible actions, the transition models, the goal test, and the path cost function. The initial state defines where the search begins, the action describes what moves are possible. The transition model explains how each action changes the state. The goal test check whether the desired objective has been achieved. The path cost function calculate the cost of moving from one state to another, helping determines the best solutions. Proper problem formulation is extremely important because even the most advanced algorithm cannot work effectively if the problem is not defined clearly and precisely. Next, move to the uninformed blind search strategies. Uninformed search strategies, also known as blind search method, are techniques that solve problem without using any additional knowledge about the goal state. These algorithms do not have guidance or estimation of how close a state is to the goal. Instead, they explore the search space systematically according to predefined rules. Because they lack heuristic information, They may explore many unnecessary states before finding the solution. The main uninformed search strategy include breadth first search, depth first search, depth limited search, and iterative deepening search. These methods are simple and easy to implement, but their efficiency depends heavily on the size of the space search space. In large or complex problem, uninformed search may require significant time and memory. Now come to the breadth first search. Breadth first search is one of the simplest search algorithm in artificial intelligence. It explores the search tree level by level, meaning it first expands all nodes at the current depth. Before moving to the next level, BFS uses a queue data structure which follows the first in, first out principle. This ensures the nodes are explored in the order they are generated. One major advantage for BFS is that it is completely, meaning it guarantees to find a solution if one exists. Additionally, if all actions have a equal cost, BF will always find the shortest path, making it optimal in such case. However, its biggest disadvantages is high memory consumption because it must store all nodes at each level before moving deeper. Therefore, BFS is suitable for smaller problem but may become inefficient for very large search spaces. Now, depth first search DFS. Depth first search takes a different approach compared to BFS. Instead of exploring level by level, DFS explore one branch of the search tree as deeply as possible before backtracking. It uses a stack data structure which follows the last in first out principle. This means the most recently generated node is explored. First TFS require much less memory than BFS because it only needs to store nodes along the current path. However, it is not guaranteed to find the shortest solution. So, in some cases, DFS may even get stuck in the infinite loop if the search space is very deep and contains cycles. Therefore, while DFS is memory efficient, it may not always be the best choice when optimality is required. Next is depth limited search. Depth limited search is improvement over depth first search. In this method, we introduce a fixed depth limit that restricts how deep the algorithm can explore. This helps prevent the problem of infinite loop or excessively deep searches. By setting a limit, we control the search depth and avoid wasting time exploring irrelevant path. However, if the solution lies beyond the chosen depth limit, the algorithm will fail to find it. Therefore, selecting an appropriate depth limit is crucial. Depth limited search is particularly useful in problem where the search space is extremely large or potentially infinite. So, next is iterative deepening search. Iterative deepening search combines the advantages of DFS and BFS. In this approach, we repeatedly perform depth limit search with increasing depth limit. First, the algorithm searches with depth limit 0, then 1, then 2, and so on until the goal is found. This approach ensures completeness like BFS while maintaining the low memory usage of DFS. Although it may seem repetitively, it is actually very efficient in practice because most of the nodes are located at the deeper level of the search tree. Iterative deepening is widely used in AI systems especially in game playing and large search problems, because it balances time and space complexity efficiently. Now, move to the informed heuristic search strategies. Informed search strategies, also known as heuristic search methods, improve open information uninformed search by using additional knowledge to guide the search process. These algorithms use a heuristic function, typically denoted as HN, which estimates how close a given state is to the goal state. By heuristics, the algorithm can prioritize more promising path and avoid unnecessary exploration. This significantly improves efficiency and reduce computation time. Two important uninformed search algorithms are best first search and A star algorithm. The efficiency of these algorithms depends largely on the quality of the heuristic functions used. The next is best first search, BFS. This search expands the node that appears to be the closest to the goal according to the heuristic function. It evaluates node using an evaluate function, often written as function fn equals to hn, where hn is the estimated distance to the goal. By always selecting the most promising node, best first search can reach the goal faster than uninformed method. However, it does not consider the cost already incurred to the reach a node, which may lead to suboptimal solution. Therefore, while best search is fastest in many situations, it does not always guarantee optimality. Now, A star algorithm. The A star algorithm is one of the most powerful and widely used search algorithms. In artificial intelligence, it combines the strength of the uninformed cause search and heuristic search. The evaluation function A star is defined as F1 equals to Gn plus Hn, where Gn represents the actual cost from the start node to the current node and Hn represents the estimated cost from the current node to the goal. By combining these two values, A star balance exploration and efficiency. If the heuristic function is admissible, meaning it never overestimated the true cost, then A star is guaranteed to find the optimal solution. Because of the property, A star is extensively used in pathfinding, robotics, navigation, and real world planning system. Now, come to the game playing in AI. Game playing in artificial intelligence involve decision making in competitive environment. In such problem, these are usually two players who takes turn making moves. The objective is not only to achieve a goal but also to prevent the opponent from winning. For example, include chess, tic-tac-toe and checkers game playing problems are different from simple search problem because the outcome depends on the action of both the player. Therefore, AI system must anticipate the opponent's moves and make decisions accordingly. This requires adversarial search technique such as the minimax algorithm. Now discuss about the minimax algorithm. The minimax algorithm is a decision making algorithm in two player game. It assumes that one player is trying to maximize the score while the other is trying to minimize it. The algorithm constructs a game tree that represents all possible moves starting from the terminal node. It assigns value based on the outcome and then propagate these values upward. Through the tree, the maximizing player choose the move with the highest value, while the minimizing player choose the move with the lowest value. The key assumption in minimax is that the opponent always play optimally. Although minimax guarantees optimal decision, it can be computationally expensive because it explores many possible moves. Now discuss about the alpha beta pruning. Alpha beta pruning is an optimization technique applied to the minimax algorithm. It reduces the number of the node that need to be evaluated in game tree without affecting the final result. The algorithm keep track of two values, alpha which represents the best value that the maximizing player can guarantee so far, and beta which represents the best value that the minimizing player can guarantee so far. If at any point beta becomes less than or equal to alpha, the algorithm stop exploring that branch because it cannot influence the final decision. The significantly reduces competition time and allow the algorithm to search deeper level in the same amount of the time. Now, summarize all the unit 2. To conclude this unit, we studies how artificial intelligence system solve problem using structured search techniques. We begin with state space representation and problem formulation, which are essentially for defining problem clearly. We then explored uninformed search method such as BFS and DFS, followed by uninformed search and informed search method like best first search and A star. Finally, we discussed game playing algorithm including minimax and alpha beta pruning, which enables AI system to make intelligent decision in competitive environment. These search techniques form the foundation of intelligent reasoning, planning, and decision making in artificial intelligence. Thank you.